Welcome to Blue Marble Geographic's Ask the Experts. I'm Rachel Landry, and today I'm joined by my colleague, Sam Knight, the Director of Product Management here at the company. Today, Sam will be talking to us about best fit calculations in Geographic Calculator. All right, Sam, take it away.
Thank you, Rachel. Today we're going to be taking a look at the best fit job in the Geographic Calculator. This is a very specific job, and it really has no substitute when you need this particular function. So what we're talking about here is creating a relationship between a survey grid on the ground and a geodetically based coordinate system like lat long or anything with a projection. Where we have these arbitrary ground systems are places like mining operations, some oil field, construction sites, airports, a number of different common uses for these things. The need for them is because they are based on ground coordinates. They have no geodetic basis. So what we're going to do is take a set of these ground coordinates. They're going to be control points that are very tightly surveyed within this coordinate system. We have matching coordinates for those, and in the case of our data here, they're based on UTM zone 15 coordinates. Doesn't matter what coordinate system they're in, that just happens to be what our data is in. This coordinate system is a real grid. It simply has been transposed to a different location to protect the original source. Spatially, it's all relatively in the same relative positions to each other. So what we have in this data is a spreadsheet, and it just happens to be a Microsoft Excel sheet. And within the data, we have local coordinates, 2 columns, northing and easting, and then 2 more columns of UTM 15 controls. So that's UTM zone 15 north on WGS 84 in meters. Again, the geodetic coordinate system doesn't matter. You can use anything on these. There are some placeholder columns in the Excel sheet. Really, all you need to start are those 4 columns of coordinates. We have a column labeled point use, and that's going to act like a switch for whether we include or exclude a particular control pair in the overall model. And then we have error columns for what are called residual errors, and that is the individual error for the individual control pairs within that larger model. There are 4 sets of those, 2 for the northings and eastings in the forward direction, going from local to the geodetic system in the transformation, and then 2 more for the northing and easting in the reverse direction, coming back from the projected system to the local grid system. And what I'm talking about there, forward and reverse, those are the mathematical directions they're going. This is going to be a 2-way transformation when we're done. So to set this up, we basically just load in our spreadsheet, and we set the coordinate system for what our controls are based on. So in this case, it's WGS 84, UTM zone 15. And then on the outside of that, the fitted coordinate system info on the right, it says point database best fit, and that's just simply a template placeholder. This is going to be where you give it a name. So whatever is appropriate for your local coordinate system. And in this case, I'm just going to call this Sam's mining grid. So all of the drop downs at the bottom, these are going to be where we set the matching columns in the spreadsheet. So the use flag, that is again the one labeled point use in my sheet. The specific name of that column doesn't matter. We're going to use the drop down to just match up whatever they are. The name column is optional, and in this case I don't actually have names for these control points. They only have the number of the row that they are in the spreadsheet to identify them, and that's fine. The math transform is probably one of the most significant operations to choose on here. Most folks are going to just simply use an affine transformation, the first one in the list there. This is a simple linear polynomial equation. The mathematics for it resemble basically 2 line slope equations, if you remember basic algebra, one for x and one for y. We'll be solving based on 6 variables. You don't need to do any of that. That's what the interface is going to do for us. The basics requires a minimum of 3 control points, but more practically in the field, we're going to be using between 20 to 30 for an average size mining grid. Beyond that, if we start stretching many miles and the coordinate system spans over the horizon, then we'll start stepping up into the higher order polynomials from second all the way up to 5th if we're doing very large regions all the way up to the size of a country or subcontinents and things like that. For the local coordinates in the middle here, these are going to be our ground coordinates. So mine are named local north and local east. The names of those columns, again, doesn't matter. The base coordinate systems are our geodetic controls. So UTM 15 north and UTM 15 east. Just likewise, whatever those are named in your spreadsheet is fine. Now the error columns, I'm just going to set these all up here to match. So I have a column for the north error, east error, north reverse error, and east reverse error. If you don't put placeholders for these in your Excel sheet or whatever spreadsheet format you're using, that's totally fine. If you notice at the bottom of those drop downs, there is a selection down there to add a new column, and that's where you can add those placeholders yourself. The last setting here is to flag errors greater than some multiple of either the RMSE, which is root mean square error, or the input units. So what we typically recommend is using the multiple of the root mean square error, because if you do that, it will statistically scale with the overall error associated with your grid. If you use the input units, it will be much more rigid, and you don't necessarily know what that error is going to be the first time through. It allows you to fish for a certain level of accuracy overall within the model. Some people want to be more accurate than, say, 10 centimeters. Some people want to be accurate more than, say, 1/10 of an inch. It depends on who you are, what type of coordinate system you're working with, and the overall accuracy of the control network that you're feeding in. So I typically work with the default setting here of 3 times the root mean square, and then you can always update that if you want to tighten it up in subsequent derivations. Once we have all of these things set in place, we just go over down to the right there and hit the process button. When you hit process, it calculates very quickly. You'll see in the table at the top, a lot of very, very small numbers are going to appear. This is going to depend entirely on the tightness of the survey that you're feeding into this. So if you have something very old that was done just roughly and quickly to a low level of survey accuracy, you're probably going to see bigger errors in there. And if you're doing something based on modern equipment, very, very precise efforts being put into the field work, you're going to see very small numbers in there. Small numbers are good, big numbers are generally bad. There's a lot of very little numbers here to look at, though. So we have an alternate view to take a look at these, and it's called the error plot. So the tab for that, you'll see it's right up at the top left next to the best fit tab. And what this does is it graphically plots out, the green dots here are the locations of each individual control pair. And there's 2 directions. There's that forward and inverse or reverse that we mentioned before. So forward with the tails going one way, and reverse with the tails going the other direction. Those represent the 2 different directions through this mathematical formula that we just derived. The tails coming off of the points are a visual rendering of a relative error. These are not absolute one-to-one relationships. So the tails look very, very large. It looks like there's a lot of problems in here, but those are actually being multiplied by some number that we derive in this process to help make a visual indicator on the screen. If you look over on the lower right, you'll see the exaggeration factor, and in this case it's about 3,800, which means we're taking the actual errors, multiplying them by 3,800 to make a tail long enough for a meaningful distance on the screen. So don't worry when you see a very large tail off of there. It's just to draw your eye to the very largest of the errors. So very quickly here on screen, we can see that we have a few of these points that have much longer tails than the rest, and those are the ones we want to pay attention to first. First, I'll click on this one right here. You'll see it blink red. And that one is identified as point number R20, which means row 21. Row 21 in that data has a larger error associated with it. If we look down in the specifics, we can see that the X error on that is about 26 centimeters, and the Y error is very, very tight at less than a millimeter. So there may be some issue with the X component of that coordinate. Maybe it was surveyed poorly. It's still quite small, so maybe it was just simply a bad signal on the GPS or some small surveyor's error. We could take that out of the model and reassess the rest of them in an iterative process. So to do that, we might go back to the Best Fit tab, scroll down to R21 in the grid, and in that point use flag column, we're going to select that and change the 1 to a 0. and that will eliminate that from the overall model. Once we do that, we need to hit process again, and that will redo the calculation, and I'm just going to hit yes to overwrite the previous calculation. You'll see all of the errors stay very low. This is already a pretty tight grid. And when we go back to the error plot now, you'll see that point number 21 has changed its representation. There's a legend up here in the top left to take a look at which are used in the model and which are statistical outliers and so on. So removing that one from the grid, you'll see we still have a couple others that seem like they're pretty large. Maybe we could go back and remove those one at a time and compare the overall model. But if we take a look at the RMSE, that is the root mean square error over here, you'll see the fit for the entire grid is just over 8 centimeters. So that's still a pretty tight grid for this operation, and for the purposes of the work that this coordinate system would go into, that's more than accurate enough, so we don't actually need to do that. This grid would be ready to go, and to maintain that in the list, this is where that name field comes in. So that spot that I entered in, Sam's mining grid, if we go up under the data source menu into coordinate system definitions, you'll see there's the category in here called fitted. This is empty out of the box. This is where all of your derived best fit grids will go. And so there you'll see just a single entry. Right now it says Sam's mining grid. You'll see it's not locked, and the text on it is blue, indicating that it's a custom coordinate system that you control the parameters of. If we open that up, you'll actually see all of the coefficients to fulfill the equations that we need to go for the forward and the reverse direction. That's what the forward and back columns are in there. This would be a good place to add some additional notes. You could fill out the remarks on the identification tab to mention maybe something like how many points were involved in your solution, who the technician was that did the work, any historical information you want to keep available in your organization to properly identify that coordinate system. It's all optional, but it's a very good idea to fill out that kind of data. Once you have checked this out, you think everything is good, the first thing you want to do is to quality control the transformation by putting in some other data and checking it out. So taking maybe your control data, doing some conversions on that, and just validating it. Once you have that, it's in your coordinate system database forever. You don't have to do this process every time you use it. It is a permanent coordinate system, and you can apply it on any of the other jobs throughout the geographic calculator, from the interactive conversions through the spreadsheets, vector files, raster files, and so on. It acts just like any other coordinate system.
Sam, thank you so much for sharing that workflow with us. I know our users will find it very interesting. To learn more about Geographic Calculator, please visit bluemarblegeo.com today. And as always, thank you for joining us for Ask the Experts. We hope that you'll join us for our next episode.